Hello, scholars. We are back with a lot more information about precipitation reactions. So in the last video, you saw how to write net ionic equations for double replacement reactions, showing only the parts of the reaction that are actually participating. Today we're going to look at the stoichiometry behind these reactions and how we can use the concept of limiting reagents to show the quantity of precipitate formed or quantity of ions remaining after reactions have been completed. So this first little snippet here, in an AP chemistry laboratory, students were given 2 unlabeled beakers and told that one of them contained 1 gram of solid calcium carbonate and the other contained 1 gram of solid silver nitrate. They were told to devise an experiment to identify which compound was which. A student did so by adding 50 milliliters of distilled water to each beaker. Describe their observations that allowed to identify each compound. So think about this for a second. So if you remember your solubility rules, all nitrate compounds are soluble. So when they added the distilled water to each beaker, the silver nitrate would fully dissolve and the calcium carbonate would not. So that's how they would differentiate between the two. Okay, now on to the stoichiometry. When you are looking at these problems, you want to either write out the net ionic equation or at least use context clues in the problem to determine what the net ionic equation would be, determining a limiting reagent if necessary, and then answer the question that's being asked. So this question here we're going to do in multiple parts. So we have a solution of sodium phosphate and we have a solution of lead 2 nitrate, assuming that when we combine the two solutions that their volumes will be additive. So we are given the balanced equation, which you would be given on the any AP question, you'd be given the balanced equation. So we want to know the grams of precipitate that will form. So our precipitate is the lead 2 phosphate, right? Nitrate compounds are going to stay soluble. So our net ionic equation would be based off of lead and phosphate. So this is a limiting reagent problem because you're given 2 different concentrations and quantities of 2 different solutions. So what we need to do is figure out which reactant was limiting and then from there determine how much of the lead 2 phosphate could actually be produced. I'm going to give you the gram formula mass of the lead 2 phosphate. It's 811.54 grams per mole to speed things up. So remember that molarity, the unit of the capital M can be expanded as moles over liters, so we can use it as a conversion factor. So this concentration is actually 0.30 moles over liters. So what we will do here is start out with the sodium phosphate. So we will take that volume and make it into liters. And we want to make sure we put the substance as well. Then we want to multiply that by the molarity because we want to get to moles. So now we have moles of the sodium phosphate. So now we want to get to moles of product, the precipitate, because that's what we're looking for. So using the coefficients. And then take it to grams right away so you don't have to do that step after the fact, in my opinion, since we have the gram formula mass already. Okay, so units will cancel, and we're left with grams of the substance. And we're going to do that again for the lead 2 nitrate solution, same thing. Okay, so now we have moles of the lead 2 nitrate. We'll change that into moles of the precipitate using the coefficient. and then take it to grams using the gram formula mass. And then all we have to do is plug each of these into our calculator. To figure out the possible masses. So for the first one, it's approximately 1.22 grams of product or precipitate, and the second one is 1.08 grams of precipitate. So because the 1.08 is the smaller value, that would mean that the lead 2 nitrate was limiting, and that is the actual mass of precipitate that would be formed, the smaller amount. Okay, the next portion of this question, we have the same solution mixture that we're making, we have the same chemical reaction occurring, and now what is the concentration of nitrate ions left in solution after the reaction is complete? So here are the nitrate ions, and since nitrate, we established earlier, was not part of the net ionic equation because it's aqueous the entire way through, the nitrate ions actually are not reacting at all. So whatever nitrate ions we started with is going to be equal to the quantity of nitrate ions that we ended with. So all we really have to do here is work with the lead 2 nitrate compound that had the nitrate in it and determine how many nitrate ions we had in the initial solution of lead 2 nitrate, and then what that concentration's molarity, would be once you've combined the two solutions together, keeping in mind that when we put them together, we're just going to add their volumes. So again, we're going to start with the concentration, or we're going to start with the volume, so 0.02 liters of the lead 2 nitrate, that's the volume that we started with, and the 0.2 mole per liter solution. So now we have moles of lead 2 nitrate. Now all we have to do here is see how many moles of nitrate are in a mole of lead 2 nitrate, and the only thing we have to do here is just count the quantity of nitrate ions in the formula. And there are 2 nitrate ions in the formula for lead 2 nitrate. So now we have the number of moles of nitrate ions present in the solution, which is 0.008 moles. Now the question's asking for the molarity or the concentration, so we need to divide by liters. Well, how many liters? The number of liters will be the sum of the two solutions once we add them together. So 30 milliliters, which is equal to 0.030 liters. So when we do that problem, we come up with 0.27 molar concentration. So that one's a little bit less work. So the last part of this question, we have the same scenario again, and now we're looking for the concentration of phosphate ions left in solution after the reaction is complete. So there's actually 3 parts to this. This is a little trickier. We need to first figure out how many moles of phosphate are available at the beginning. We then need to figure out how many moles of phosphate are used to make the precipitate. And then from that information, but based on what's left, we have to calculate the concentration of PO4 left. And there's going to be leftover phosphate ions because we established that the lead 2 nitrate was the limiting reagent. So that means it's going to run out. All of the lead ions are going to go into making that lead 2 phosphate precipitate, whereas the sodium phosphate was our reactant that was in excess. So there's going to be phosphate ions left over. So that's what we need to figure out. So first, let's figure out how many moles of phosphates are available at the beginning. So we use the information for the phosphate compound that we have. So we have 0.010 liters of the sodium phosphate times 0.3 moles per liter. And then we just have to see how many phosphates are in that original quantity. So in 1 mole of sodium phosphate, you just count your phosphates, we have 1 mole of phosphate ions. So that comes out to 0.003 moles of phosphate ions are available at the start of this process. Okay, the next part is to figure out how many phosphates went into making the precipitate. So we look at the components that contributed to that precipitate. So the lead 2 nitrate solution, lead 2 nitrate, all of those leads are going to go into making the lead 2 phosphate solution. So we want to figure out that part. 2 moles. And then using the balanced equation, which was on the prior slide, when we make the precipitate of the lead 2 phosphate, again, this is the coefficients from the balanced equation, 3 moles of the lead 2 nitrate are used. So now we have lead 2 phosphate, and we want to figure out how many moles of phosphate are in the lead 2 phosphate. So we count. There's 2 phosphates in every lead 2 phosphate. When we do this calculation, we get 0.00267 moles of phosphate are in that precipitate. Okay, so we had 0.003 moles available. We used 0.00267 moles. So we can calculate how much is left floating around that did not get put into that precipitate by subtraction. Okay, so that's how many moles of phosphate are left floating around in that container. Now we just have to get the concentration of that by dividing by the combined volumes of the solution, and you get 0.011 molar concentration. I think that's the toughest part of this question, is figuring out how much is left over, but it's a pretty standard process of figuring out how many of those ions were available at the beginning of the process, how many of those ions were used to make up the precipitate during the process, find the difference between that, and calculate the concentration. A couple last things about precipitation reactions or these double replacements. Some double replacement reactions don't give you what you'd expect from like that swapping of ions. If you have a compound that's a carbonate reacting with an acid, you're going to, if you just did the straight swapping, you'd say, okay, calcium chloride and then carbonic acid, which is H2CO3. H2CO3, carbonic acid, is not very stable, so it's going to break apart right away, and it's going to give you CO2 and H2O. You did a reaction similar to this in the physical chemical changes lab. You used sodium carbonate and reacted it with hydrochloric acid. And one of the observations that you made when you did that was that there was bubbling. The bubbling was the production of the carbon dioxide gas from the decomposition of the H2CO3. And these are just a couple examples of that. So anytime you have something with a carbonate or a hydrogen carbonate or bicarbonate ion reacting with an acid, though you will see that as products, you'll see gases being formed. It's not something that you really have to deal with predicting. You don't really have to predict products. But if you were asked, why would a formation of bubbles occur, you would say that, just predict the products. You would expect to see H2CO3, but being that that's a weak and unstable acid, it's going to break down. All right, we're going to work on a lot of these precipitation stoichiometry problems in class together. You'll get the hang of them. And we'll put them into the context of some actual old AP free response questions.